Welcome to Lecture 15 on Wallace's Theorem. I'm battling my neighbor's leaf blower at the moment, so if it sounds like I'm kind of half yelling, there's kind of a reason for that. Alright, so here we go. If A and B are subsets of topological spaces X and Y, respectively, then the Cartesian product of A and B will be a subset of the Cartesian product of the topological spaces X and Y. And if you think about it, there are a couple different ways we could topologize the Cartesian product of A and B as a subspace of X cross Y, right? Well, one thing, we could just look at the subspace topology of the product, but on the flip side, we could take the product topology of the subspace topologies of A with respect to X and B with respect to Y, and Minetti argues that those essentially lead to the same topology for the subspace A cross B. And a result which sort of informs us about how that all works for a case we're interested in is given here by Wallace's theorem. So if X and Y are topological spaces, A is a subset of X, B is a subset of Y, and these are compact subspaces. And if you've got an open set W which contains A cross B, then in that context there exists open U, a subset of X, and open V, subset of Y, such that A is contained in U, B is contained in V, and the Cartesian product of U and V are again in W. So essentially this means that, let's see here, so if you've got some set that's open, if you've got some, Benjamin's at it with me right here right now. If you got some set W which is open in the Cartesian product, then you can inside that put something that's in the product topology of the subspaces. See, because U open in X and V open in Y, like this, would be the kind of things we'd use to form open sets in A and B with the subspace topology, right? Something like that. That's not quite it, but anyway, here's Wallace's theorem. All right, so here's the proof. Let A be an element of A. Let A be the singleton A. For any B, we're going to assume the preconditions here of Wallace's theorem, right? And so for any B and B, there exist two open sets, UB in X and VB in Y, such that the pair A comma B is in UB cross VB rather, subset of W. This follows because we're assuming W is open, and because we're assuming that A cross B is a subset of W, right? And well, notice that if we look at the open family of such sets, VB such that B is in B, that covers B. And if that's true, well, B is compact, which means that if we take an open cover of a compact set, there has to be a finite subcover, like so. And then we can define open sets by picking those ones and looking at U as the intersection of, UB1 through UBN and V of VB1 through VBN. Then we have that the singleton A cross B is a subset of this U and V so constructed, and that is itself a subset of the, union of the Cartesian products of VBI and UBI and VBI, which again is a subset of W. All right, so then the proof continued here. Yes, continued. Yes, Benjamin, continued. You think that's a funny word, huh? Okay. If A is an arbitrary compact set, then by the last page's argument, we've shown that for any A, there exists open sets, let's say UA and VA, such that the singleton A cross B is a subset of the Cartesian product of these dudes, which is in a subset of W. But then we can use that, basically kind of recycling the trick that was on the last page. The set of UA such that A is in A, well, that forms an open cover of A. And as such, there exists, because A is compact, we're assuming A is compact, there exists a finite subcover, right? And as such, we can form U as the union of all these guys, and V as the union of all those guys, and that gives us that A cross B is a subset of U cross V, which is a subset of W. And anyway, all of this whole argument it's all in Manetti. I'm just repeating it here for your benefit. So if there's any errors in the argument, it's probably my fault. But anyway, okay, sorry. Any compact subspace in a Hausdorff space is closed. Let me repeat that. Corollary. Any compact subspace in a Hausdorff space is closed. Remember, Hausdorff space is a space in which we can separate points with open sets, right? So let X be Hausdorff and K a compact subspace, all right? Then we may show K is closed by proving that the complement of X by K is open. How do you show that the complement of X by K is open? Well, you demonstrate that if you pick X which is not in K, you can find an open set U which contains X and is a subset of, X is an element of U, and U is not in K, right? U is an element of the complement of X by K, which is to say that U intersect K is empty, all right? But if you notice that if we take the set, the singleton X cross K, that does not intersect the diagonal, right? That's true because X is not in K, so we don't have X comma X in here. It's impossible, right? By construction of the little x. And as such, I think this page would be improved if I don't know, when I'm using a point, and I've got lots of x's floating around, sometimes it just makes me feel better if I put some...
Hello.
Yes, hello, Benjamin. Why are you saying hello to us?
To bother the video.
You're just bothering my video? You think that's funny, huh? I think that only would be funny to a 5-year-old. How old are you?
5.
Oh, you're 5. That's what it is. I knew it. If I had put these sub-knots on it, we can clearly see this is a point. All right. There we go.
Echo.
There's no echo here. What are you talking about?
Echo.
Oh, goodness gracious. What have I started? All right, so observe that...
Echo.
Benjamin, please don't be so loud. X naught... Again, the singleton X naught cross K does not intersect the diagonal of X cross X, but X is Hausdorff, right? Which means that, let's see here, what does that mean? That means, well, the X Hausdorff doesn't mean this just yet. Let's see, or does it? So I say the singleton X naught Cartesian product with the compact space K is a subset of W, and I'm saying that W is equal to the complement of the Cartesian product of X with itself by the diagonal. This, my friends, is open because of Theorem 3.69, which says that if X is Hausdorff, the diagonal is closed, which is to say the complement of the diagonal is open. So this is my open set, which contains this singleton cross the compact subset rather. So then we can apply Wallace's theorem and select open in U and V in X, for which the singleton X naught cross the compact space is a subset of U cross V, which is a subset of W. And then you notice that X naught's an element of U. U intersect K by construction is empty, and therefore we find K is closed. So there it is. Any compact subspace in a Hausdorff space is closed. All right, so moving on here.
Move on.
Yes.
Move on.
I'm moving on, Benjamin. Yes, very funny, very funny.
Move on.
I don't quite understand your comedy, Benjamin, but I'll allow it. Let's see here. Corollary 4.49. Let X and Y be topological spaces if X is compact and pi is the projection onto the second component of X cross Y, defined by pi X comma Y equal to Y, then pi is a closed map. If X and Y are compact, then X cross Y is compact. And I guess we could leave the we could leave that 2 alone, maybe that pi alone, but I think I'm going to add a 2 to it because it just feels right. Because it's the second projection there, you know. Pi 2 is a closed map, since there's 2 of them. Alright, so,
Two of them.
yes, Benjamin, 2 of them. You're very goofy today, Benjamin. Alright, here we go. So, following Minetti, page 77, points out that if we have a, so let's see here, we're trying to prove it's a closed map, right? To prove that that pi 2 is a closed map, we need to take an arbitrary closed set in the Cartesian product of x and y, right? And show that that maps to a closed set in y, all right? So let's see how that goes. So take a closed set, and if the projection, if pi 2 of C is all of y, then, well, the whole topological space is by definition both closed and open, right? So certainly y is closed, and in that case, pi 2 would be a closed map. Great, we've got it. So the other possibility is that pi 2 of the closed set is not equal to y, right? Then that would mean that there exists y, which is not in the projection of C. And so then we seek to show that there exists a neighborhood V about y. Yes, a neighborhood, such that V intersect the projection of C is empty. All right, because then that would show that the complement of the projection of C is open, which would then show that the projection of C is closed, right? Benjamin. Yeah, very funny. So we have X, which is assumed compact. We have Y, which is a singleton, that's compact. All right. And you're a kitty cat? That doesn't even make sense. And then, so that's a subset of X cross Y, complement by C, because Y is not an element of C, right? So, well, by construction of Y, all right? And I should just say that, by construction of Y. But C is closed, which means that X cross Y minus C is open, right? So we've got an open set that contains the Cartesian product of these two compact sets. So we're thinking of this like the A cross B in Wallace's theorem. There exists an open V, which contains Y, and such that X cross V intersect with C is empty. And consequently, V intersect the projection of C is empty. And what's that tell us? Oh, that tells us that the complement of the projection is open, which then says that the projection of C is closed. But C being an arbitrary set, we have proved that the pi 2 is in fact a closed map. Benjamin, buddy, I need you to be a little bit quieter, okay? All right. So part 2 here, theorem 4.44 says that the closed. So what we're trying to prove at the moment is that if X and Y are compact, then the Cartesian product of X and Y is compact. Okay. So here's a proof given down here. Recall theorem 4.44 in Minetti says a closed map F, let's say from X tilde to Y tilde with Y tilde compact, then if the inverse image of the singleton Y is compact for every Y in Y tilde, then X tilde is compact. All right, so we can apply theorem 4.44 in the case that F is equal to the second projection map, and the domain is X cross Y, the range is Y, noting that the inverse image of the singleton Y is the whole of X cross that singleton, right? And this is compact because, let's see here. We had assumed I think how I know that this is compact. Oh, we're assuming X is compact. So if we take it's fairly obvious that there's a homeomorphism from X to X Cartesian product with a singleton. Right? Like, I'll leave that to you guys. But if you take a set and you just take every point in the set and just Cartesian and just, pair it with a single Y, it's really just an annoying notation for X where you're taking every point in X and pairing it with Y, the same Y, not a different Y. And so there's an obvious one-to-one bijection between the set X and this set, namely just P maps to P comma Y, the homeomorphism I'm talking about, let's say psi, would be this. You can prove that this is a homeomorphism, and if it's a homeomorphism, the image, it preserves compactness, yeah? So psi of a point P in X is simply mapped to P comma Y, right? And so like psi inverse, the mapping, so a typical point is P comma Y, and it just maps back to P. Okay, so I probably could write that in terms of pi 2 anyway, but let me just leave it at that. So these, clearly X and X cross the singleton Y are homeomorphic, and X is compact, so this is compact, which is my claim. But then we can apply Theorem 4.44 to then get that X tilde, which is X cross Y, is compact. So, hooray, there it is. So here we go, corollary 4.50. A subset A of Rn is compact in the Euclidean topology if and only if A is closed and bounded. So here we go. So if A is closed and bounded, then that means that there exists an A such that you can put it in like I don't know what we want to call this thing, the plus or minus an cube. So this is like a cube of side length 2a and an n cube, it's a hypercube or whatever. But if it's closed and bounded, that means that definitely we can bound it by this bounding n cube. And but what else do we know? We also know that minus a to a is homeomorphic to 0, 1. Therefore, minus a to a is compact, and you can inductively extend corollary 4.49 to see that the n-fold Cartesian product of a compact set is again compact. And, okay, but a closed subspace of a compact space is compact. I believe we just proved that, right? So we're assuming A is closed. It's a subset of a compact space. Therefore, A is compact, right? This is if and only if, so we need to go the other direction as well. Conversely, if a subset of Rn is compact, right, then the map D0 from A to R, given by, take the norm of the point using the Euclidean norm. So like the formula for this is the square root of x1 squared plus x2 squared plus plus xn squared, square rooted, square root of that sum, the usual Euclidean norm, right? So this map is continuous, and since this is a continuous map and it has a compact domain by assumption, right? That means it has a maximum by the extreme value theorem. Thus, as such, A is bounded, but Rn is Hausdorff, so corollary 4.48 provides that A is closed, because corollary 4.48, which was like 10 minutes ago, what did it say? It said that any compact subspace of a Hausdorff space is closed. So we've got a compact subspace of a Hausdorff space is closed, and this argument right here on the distance function gives you the bounding. right? Using the extreme value theorem on that continuous function. So there it is. Application. Finally, an example. Woohoo! And this one we'll use in future lectures. This one's actually kind of important. The n sphere, Sn, and the closed balls, Dn, are closed and bounded subsets of Euclidean space. Therefore, the n sphere and the n disk are compact subspaces. And finally, corollary 4.52, let f from x to y be continuous, x compact, y Hausdorff, then f is closed. If f is also bijective, then f is a homeomorphism. All right. Let's see here. So here's the proof. Let a subset of x be closed, then A is compact, and f of A is compact. All right. In Hausdorff y, which implies that f of A is closed by corollary 4.48. Right. And wait a second here. So starting with a closed subset, right? If you've got a closed subset of a compact space, it is compact, right? So that's how we get A is compact. But then the continuous image of a compact set is compact. And it's not just compact, it's compact in a Hausdorff space Y. But then if we have a compact subset of a Hausdorff space, that means it's a closed subspace by corollary 4.48. But we've just shown that the image of a closed set is closed, therefore F is a closed map. And then the corollary follows, since a continuous and closed bijection is a homeomorphism. So, all right. So that's the section on Wallace's theorem. I think the main takeaway here is, well, I mean, some of these lemmas and corollaries and such are useful for future sections, but certainly this is the biggest result, is that the n sphere and the n disk are closed and bounded subsets of Euclidean space, and as such they're compact subspaces. Okay, so anyway, that's it for this one. Next up is a much lengthier lecture on topological groups. There I have added a fair amount to Minetti. Here I think I have added almost nothing. So my apologies if that is disappointing, but you know, it is what it is. So thanks, guys.